In this section, we're going to be looking at the addition rule of probability. So it's quite a lengthy section, and in order to work through the problems thoroughly and go over each point in detail, so feel free to pause partway through and take a break if you need to. Now, when we're using the addition rule of probability, we're going to be using the classical approach to probability formula. So in order to use the addition rule of probability, you have to first determine that we are looking at the classical approach situation. When that is the case, then we can use the formula you see here on the bottom. So when the addition rule of probability is an event combining two or more simple events. So when we've got two or more simple events, and we want to look at the probability of them being combined, we use an addition rule of probability. Notice that we cannot use the relative frequency approximation of probability. So this is where, when we're looking at the scenarios and deciding which type of formula to use, although there are a lot of similarities between the relative frequency approximation probability and the classic approach, the differences are important but subtle, but they determine then whether or not we can use the addition rule, multiplication rule, and other aspects of probability theory we'll be looking at across the next month. So, let's walk through the steps of doing an addition rule of probabilities. First, you need to identify when you're going to use the addition rule. So to do this, you need to pay attention to the use of the language and the problem. So if it finds the word or in a problem, this indicates that you're using an addition rule of probability. Now this is a different meaning in statistical language than what you see in general language. This is another one of those places where we have to notice that using a term the way it is used in daily language is not the same way that it is meant when it's used statistically. So if you're reading the word problem and they use the word or in the problem, this tells you that you're going to be using the addition rule of So the addition rule of probability, probability of A or B, equals getting the probability in a single trial of either event A occurring, event B occurring, or it can mean that both A and B occur. So we have three possibilities that are all encompassed in the probability of A or B. So make sure you've got this in your notes clearly. It's not simply event A or event B, but it also has the possibility that both event A and B are going to occur simultaneously. So, in order to solve this problem, we need to find the total number of ways that A can occur and the total number of ways B can occur, but we need to do so without counting any one outcome more than once. And we're going to see that that can be difficult when looking at particular types of scenarios. So, when we're going through and looking at using this formula, the next step we have to decide is we need to determine if the events are jointed or disjointed. So let's take a few moments and look at these two different types of events and how we would solve each of these problems. So if we're talking about a jointed event, these events are not mutually exclusive and can occur at the same time. So here you can see in this diagram the ability to have A, B, or A and B simultaneously. So for this particular example, I labeled A as being a political party affiliation, and B, not voting in the primary. So do you have a political party affiliation, and did you not vote in the primary? So we could not vote in the primary. I could have just a political party affiliation, or I could have a political party affiliation and not have voted in the primary. So all three are possible. So this is different than when we look at a disjointed event. Disjointed events are mutually exclusive and they cannot occur at the same time. An example of this would be looking at enrollment in this course. So this class actually is listed as several different options. You have Math 302, you have Business 360, and you also have Sociology 302. So in this diagram over here on the right, I've designated A as being Math 302 enrollment and Business 360 enrollment as being B. Notice you cannot be having simultaneously enrolled in Math 302 and Business 360. You'd only sign up for one of them, even though both of those classes are combined into this single course. So, thus, we could say they were disjointed events. Okay? Since they can't occur at the same time, the space in between them is equal to 0. So when we apply this to our probability addition rule formula that we have, we can see that we're going to have P of A plus P of B. And when we subtract the probability of A and B, that's going to automatically drop out to be a 0 because there is no overlap between them. So, again, we're doing probability of A. Remember, that is going to be the number of ways that A can occur out of the number of simple different events. And the same thing we're going to see for B. So let's take a look at this for a potential problem. So we're looking at independent event. There's 20 students enrolled in this course. 6 of them are in Math 302, 12 are in Business 360, and 2 are in Sociology 302. So if I randomly selected a student from the class list, what is the probability that they will be enrolled in Math 302 or Business 360? Okay, so keep in mind we're asking from this particular class list of just 20 students, right? That's the problem that we're solving here. We can see because these events are mutually exclusive, when we look at the formula I've written out here, we can see that the probability of A minus B is 0. It drops out. And this, what I've written over here on the board, is exactly how you should be setting up your problems. So again, when you're going through and getting ready to solve the problem, remember that you're going to need to label what your P of A is and what your P of B is so that you can make sense of the final solution. So here we see we have the number of ways A can occur and the number of different simple events. And we do the same thing for option B. So take a moment, pause the video here, plug in your numbers for those different options, and then let's move forward and check your answer together. Okay, you should have gotten something that looks like this. So we have a total of 6 students in Math 302, so that's the number of ways A can occur, that I select somebody who's in Math 302. We have the total number of simple events, and which is 20, that's the number of students. And we repeat the same process for option B. Doing the addition and adding them through, we see that the probability for this class of me selecting a student who is enrolled in either Math 302 or Business 360 is in fact 0.90. So that would be the probability if I have a disjointed or independent events. Now we're going to look at jointed events, and these become more complex. Jointed events can occur at the same time, and we're going to work again with our example of whether or not one is a political party affiliation and whether or not one voted in the primary. So here we can see they occur at the same time, thus we do have the overlap of A and B on the purple area in this diagram here on the right. Thus, when we're using our formula, we do not automatically drop out the P of A and B. We're going to have to add that in. So this is how this diagram relates to the formula that we're going to use. So take a moment, make sure you get that in your notes so that you can refer to it later for homeworks and exams. And then let's take this problem and work through an example to see how this is going to come together for us. All right, so here we're looking at pre-employment drug screening results that we had before. And we want to look at the probability that a randomly selected person in this screening had a positive test result or does not do drugs. So we've got the or in there that's going to identify the kind of problem that we're going to be using the additional probability. And because we are talking about randomly selecting a participant from this particular set of screenings, we can say that each simple event has an equal likelihood of occurring. So let's take a look at how we can diagram this out. Now, I strongly suggest that when solving these problems, you take the step after you've identified that you're using classical probability, after you've identified you've got an additional probability formula, after you've designated what your A and your B is going to represent, that you produce a quick diagram of the results that looks something like this. Because designating your material visually, marking off the sections of your chart, is going to be an important step and catching yourself and making the correction for not double counting. So here we can see that we're looking at the total number of positive test results is 134, and the total number of people who were not using drugs was 950, and we've marked these off on the chart. Okay, now we go through and do our probability for each of these. So our probability of getting a positive test result here is 134 divided by 1,000, so we get our P of 0.134. Remember, we're using our rounding rule to 3 decimal points. And then my probability for not using drugs is 950 divided by 1,000, which gives me a probability of 0.950. However, we have counted the people who tested positive but were not a drug user twice. We've counted those 90 people twice. So we've double counted them. So what we need to do is we need to be able to pull that amount out of our formula. So our probability of not using drugs and positive test results, which notice is the same thing as P of A and B, right, is going to be 90 divided by 1,000, which gives us 0.090. All right, now we're going to plug this into our formula here. And we're going to see that we're going to take the P of not using drugs, which is 0.950. We're going to add it the probability of positive test results, which is 0.134. And we're going to subtract out the probability of not using drugs and the positive test results because we have actually double counted that in our formula. When we go through this, we get the results that we see here below. All right. So remember, probability values range from 1, absolutely certain, to 0, as in never possible. So if you get a probability value over 1, such as you've made here, you will have made an error somewhere. Now, this is not the only way to check your errors. You can actually have double counted your probabilities and get an amount that is less than 1. So this is not a foolproof method for checking for this problem. However, if you do get something greater than 1, you absolutely have made a mistake and need to go back and check your work. All right, so to solve this problem, the possibility of getting a positive test result or not using drugs with this particular set of screening is 0.994. All right, now I want you to go through and do the same problem, a similar situation. So we're going to use looking at this data, and we're going to ask that if one of the drug screening participants is randomly selected, find the probability that the person has a negative test result or uses drugs. So you're going to go through the exact set methods we just did before to calculate out your answer. So pause the video, go through each of those steps, solving that exercise problem, and then when you're finished, turn the video back on and let's check the answer together. Okay, you should have got a probability of 0.910 for this problem. Okay, this concludes our tutorial going through using the addition rule of probability. The next video you have for this section is going to be another practice exercise. I strongly suggest you do that as well to walk through the steps so that you can be very familiar with this option until you go on to do your homeworks and your exam.